Hello class, welcome to the Stat 312 Chapter 6 Part 1 video. Before we get started, I want to caution you, in my personal opinion, Chapter 6 is the most difficult chapter in this course. I feel the stuff you did before this, Chapter 4 and Chapter 5, there was a lot of review material. And in Chapters 7 and 8, that also has a lot of review material from stuff you learned in high school, such as linear regression, and chapter 9 kind of has a nice extension to what you learn in chapter 7 and 8. Chapter 6 is a bit harder. It's pretty much all new material for you guys. And I just wanted to prepare you going in that this is going to probably be the most challenging material you learn in this chapter. Okay, so to begin, in chapter 6, we focus on how to make inferences for two or more population means. So what we do is we like to extend methods from chapter 5 to make inferences based on several populations, and we, as I kind of alluded to already, we primarily focus on population means. Unfortunately, our pooled two-sample t-test reaches its limit when we have two independent samples. So instead, we start focusing on comparing variances, and that is we compare variances between and within independent samples. And what I mean by that, and I will get into this a little more later, is we'll compare not only each of the individual samples' variances to each other, so that means we'll compare the variance of sample A to the variance in sample B, but we'll also compare just the variability of itself within each of the sample. And the method of doing this is called analysis of variance, also known as ANOVA. Now to begin with, when we do ANOVA on two populations, it is actually going to be equivalent to performing a pooled two-sample t-test with that two-sided alternative. The methodology for this chapter is applicable to both observational studies and designed experiments. And what we mean by that is observational studies are things that we can't directly measure and we have to observe. Designed experiments are where like we are in a lab and we want to test something. Methodology only is applicable when the samples are independent. Chapter 9 and Chapter 10, we cover Chapter 9, we don't cover Chapter 10. Do give us some methods for dependent samples, but that's not the focus of Chapter 6. We're only focused on independent samples. Now, at this point, we may be asking ourselves, why would we want to do this comparison of variances? Why couldn't we just do a whole bunch of two-sample t-tests and just do it on all pairs of the samples? Well, that is an interesting idea, and you're not totally wrong in thinking that. I think that's a pretty logical thought of, well, why don't we just compare each pair to each other and go from there? Well, one issue of it is the number of comparisons will rise rapidly as our number of populations increase. So if we have, say, two populations, then that's only one comparison. If we have three populations, that becomes three comparisons. But we get to the situation where we have 10 populations, that means we're going to have to do 45 comparisons. That's a lot. That's going to take a lot of time, and in statistics and in the real world, time is money. And unfortunately, there's even a further reason why we don't want to do this. The main issue is that when we have so many confidence intervals in hypothesis test, our true level of confidence really goes down. It doesn't stay consistent. So we may have constructed a whole bunch of 95% confidence intervals, but that doesn't mean them all together are 95% confident. So say we're interested in 5 populations. So this would require us to have 10 comparisons, which we can see in our previous slide. So if we wanted to construct each of our 10 confidence intervals at the 95% confidence level, this means all those confidence intervals are going to get worked. And what I mean by that is, so the probability of 10 confidence intervals worked is equivalent to the probability of one confidence interval working to the 10th power. And when I mean worked, I mean that we successfully captured that true parameter. And so again, just a little bit of review of our probability. So the probability that 10 confidence intervals work is equivalent to the probability that one confidence interval worked raised to the 10th power. And we know that the probability, we'll say, of our confidence interval working, we'll put it at 95%. And we would have to put that to the 10th power. So therefore, that would give us a whopping 60% confidence level when we're putting this all together, or there's a 60% confidence that this is actually going to work out. That's not great. That's not really what we want, and so because of that, we're going to have to use a different approach, hence why we start taking a look at ANOVA. Now, like I said, this may seem kind of odd and counterintuitive to analyze variances. When we're really interested in comparing means. But in order to give a demonstration of what we're really looking at, we're going to use this data table 6.2. And in this, we have two sets, and within each of these sets, we have 3 samples. Now, if we take a look for a second at our 3 samples, you can notice that they each have identical sample means, meaning the first samples both have a sample mean of 6. The 2 samples, sample 2s, have a sample mean of 10, and the 2 sample 3s both have a sample mean of 15. But if you were to look at that data exactly, and we were to try to put it in a box plot, you can see that their variability is actually quite different. If you think back to the dart throwing example I had talked about earlier, when we had the one dartboard A that had darts all over the board and occasionally hit the bullseye versus our dartboard B, which was much more consistent and had a bunch of darts hitting the same spot or roughly the same spot. That's kind of what we're looking at in table 6.2. We have set 1 that has very consistent results as to set 2, which doesn't. And I'm going to pull back up and allow you to take a look at the data itself again. So again, if we just pay attention to sample 1, we can see that the range of these values go from 6.3 to 5.7. That's pretty narrow when we compare it to the other sample 1 that ranges from 3.0 to 9.0. So let's start talking about some notations and definitions. Some of the notation will be an extension of what you've seen already. Some of it's going to be a little bit harder to understand. So let's talk about the purpose of ANOVA. For us, we like to compare 2 population means where t is greater than or equal to 2 based on t independently drawn random samples. We'll take samples of size n1 from our population I, where I can be 1, 2, all the way to t, and we'll have responses yij for I equal to 1 all the way to t, and j equal to 1 all the way to ni. And we'll have a total of the summation of ni responses. Ni does not require us to have all the same I. If all ni are equal, then we say the design is balanced. This course will focus on formulas for balanced design, but JUMP can handle both balanced and unbalanced data. And we let UI be the population mean for the ith population. Our hypothesis of interest in these situations is going to have a null hypothesis of mu1 equal to mu2 equal to dot 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 equal to mu t, because again, this is going to depend on how many populations we have. With the alternative that will state, and this is going to be a little bit different than what you're probably thinking it's going to be, we are going to say that at least one ui does not equal the others. Now let's take a minute to go back to slide 34 and kind of identify some of this notation, because I do understand that this is a bit new to us. So one thing it said, we take samples of Ni from our populations I. So in this case, our T is going to be equal to 3. Because we have, let me rephrase how we're saying this. So let's just take a second and just focus on set 2. Set 2 has 3 samples, and each of those samples are equal to each other with a sample size of 5. This would be a balanced design because they have the same sample size. Also, if we were trying to write a hypothesis test, our null hypothesis would be mu1 equal to mu2 equal to mu3. Our alternative hypothesis would be, same as it was written before, at least one mu-I does not equal the others. For us, the summation of Ni would be the summation of all of our observations. So each of our 3 samples had 5 observations, so the summation of Ni would be 15 because there's 15 total observations. And the last little bit of notation for this slide is going to be talking about a single observation. And for this, we're going to use that Yij notation, where I will tell us which sample we're investigating, and J will tell us which individual observation. So for example, Y32 would be 13. It is the 3rd sample, 2nd observation in that sample. You may want to practice and review looking at this notation, because the next slides, it's only going to get a little bit more complicated. So let's go back to slide 36 and make sure that we covered all the notation that we learned. So we established that we have our 3 random samples. We talked about the notation, our total number of observations. We established that our example we were looking at was balanced, and we talked about our hypothesis. Okay, so it looks like we hit all the points there. So now we can look at slide 37, which talks about more notations and definitions. Now, this table can be pretty confusing at first until you get a handle on what each of the notations mean. So for us, we need to understand that each of the rows is a single population, and we also have each treatment or factor level. So let's begin by looking at our first factor level. Notice we have our various level of observations, and again, our observations are in that Yij format. I being our factor level, J being the number observation in that factor level. For our factor level total, which is that summation of our factor level t. For the means, it would be denoted as y bar, whatever our factor level I, and then our sum of squares. This is something we haven't talked about yet, but we'll get to in a little bit. So again, looking at each factor level, we have our individual observations. Our totals are represented with a capital letter, the level of the factor, and a period, and the mean, lowercase letter, bar over it, factor level, and period. At the bottom, we have our grand total, which is represented with a capital letter Y and 2 dots. Our sample mean, lowercase letter y, bar over it, dot, dot. And then we have our grand sum of squares. So on our slide 38, I'm going to write out what some of these are. So first, let's talk about yi dot. That is the summation of j equals 1 to n of yij. And this is our factor level total. This is what we can see in our totals column. Next, we have our factor level mean. We show this as yi dot bar, and it is the summation of j equals 1 to n of yij. And I'm going to put in the corner just so we don't forget yij. Those are individual observations. All over our sample size n. This can be simplified using our above notation to be yi dot over n. And again, this is the factor level mean. And we can see this in the column that's currently labeled as means. For our third notation that we want to draw attention to, that's going to be our overall total. That's that y dot dot, and it is the summation of I equals 1 to t of yi dot, and it is also equivalent. If we want to get a little bit more specific, it is the summation of I equals 1 to t of the summation of j equals 1 to n of yij. And again, this is our overall total. Sometimes you'll hear me refer to them as grand totals instead of overall totals. Those are synonyms. And so we can find our third notation here at the bottom. Next, we're going to look at our overall mean, which can be found at the very bottom of our means column. And that is y dot dot bar, which equaled y dot dot over n times t. And again, this is our overall or grand mean. Now, the final part of this that hasn't been addressed yet is the sum of squares. And that's going to be our fifth notation. Well, fifth and sixth, I should say. So let's take a look at slide 39 to get a handle on that. So as in our two independent sample cases of Chapter 5, Chapter 6 ANOVA also relies on the idea of homosyntesticity. That is the assumption that our variances of each population is the same. So if you recall when we did our pooled t-test, I talked about how they had to have an equal variance assumption, meaning we assume that the two population variances were equivalent. That is also true when we're working with ANOVA, because all we've really done is we've just added more samples. So because of this assumption, we have to calculate a pooled estimate of our variance, just as we did before. So in order to do this, we must first calculate a sum of squares for each factor level. Our sum of squares is abbreviated with two capital letter S's, and then often we have a subscript of I, where I is your individual factor levels. And this is going to be the equivalent of the summation of j equals 1 to n of the quantity yij minus yi dot bar n quantity squared for each of our individual factor levels. And again, we can see this under our sum of squares column where we have SSI to SST. Our final little SSP, that's our pooled sum of squares. So this is each sum of squares individually, and then we need to have our pooled variance estimate, which we call our pooled sum of squares. And it's going to be equivalent to the summation of I equals 1 to t of SSI. So basically we have each of our individual sum of squares, we'll add them together to get our final pooled sum of squares. Now, to get our final part of our estimate, we will then divide our pooled sum of squares and divide it by our degrees of freedom to obtain that pooled estimate. So if you recall, when we did our pooled t-test for two samples, we had our SP squared as that n1 minus 1 multiplied by Si squared plus n2 minus 1 multiplied by s2 squared all over n1 plus n2 minus 2. This is an extension of that only for a larger population, or in other words, when we have more than two samples, or two samples will work well as well. And so SP squared in this case is equal to SSP, our pooled sum of squares, divided by our degrees of freedom, which is t multiplied by the quantity n minus 1, which we can say is further equivalent to the summation of I equals 1 to t of SSI over the same degrees of freedom. If we have a sample where we have each of our individual variances, kind of like we did in our pooled t-test for two samples, we can also use the equivalent formula of I over t multiplied by the summation of I equals 1 to t of our sample variances. Okay, so this leads us to talk about our heuristic justification for ANOVA. But at this point, I think this is a pretty good stopping point for these first part of the lecture. I highly encourage you to review your notation, and if you have any questions, please shoot me an email. Have a good night.